All right. So I don't know what the average lifetime of a patch is in the Postgres community, but I think 5 years sounds about right to me personally. So I'm very excited to hear what Daniel has for us. I think it's going to be very interesting. Daniel.
All right, thank you, and thank you everyone for coming to this talk. It does say 5-year patch mission, but it actually took 7, so I'm slightly lying. Another issue, some of you might have read the abstract, and the abstract basically says that this patch didn't get committed, and this is why. And then I jinxed myself and committed the patch, so I had to rewrite the talk to explain why it got committed. For those of you who don't know me, my name is Daniel. I work in the Postgres open source team at Microsoft. I've been using Postgres since exactly 2005, but I've been contributing roughly since 2013. And I'm a major contributor and committer on the project. This talk is about functionality that has been committed, but it hasn't been GA'd. So, I mean, anything might happen before we GA, so take that as a word of caution. It might be reverted, might not. But yeah, just as a word of caution. It hasn't GA'd, so it's not available in production yet. So what is it about? Well, it is about data checksums, and it's particularly about online changing of data checksums. But before we get into that part of the talk, let's just do a quick primer on what data checksums actually are in Postgres. So this is the page format for Postgres, which we all know about. We're particularly interested in the page header data, and in there we're only interested really in this field, the PG checksums, which contains the checksums for the data pages. And up until V18, you could only set it at initdb or offline, like taking a cluster offline using the bin PG checksums utility. And what this patch does is it brings it online capabilities in version 19 and onwards. Checksums are on by default since version 18. Now, mileage may vary in distributions. Some distributions may have had them on by default before 18. Some may still have them off by default. I don't actually know. But from us, from the canonical source of Postgres, they are on by default since version 18. And they are verified when reading a page, and they are calculated when writing the page. So what about online changing of data checksums? Because as I said, up until V18, you could only do it during initdb or with an offline utility. So to start with that, we have to go back in time a bit. We have to go back all the way to 2017, where this sort of takes a start. And Magnus was writing an email. And he wrote an email to hackers where he asked the question, is it time to enable checksums by default and give initdb a switch to turn it off instead? And there were some wildly different opinions on whether that was a good idea or bad. Mostly, it was considered to be a fairly bad idea, given the overall tax on the system that the checksums do add. So he went back and wrote another email just the other day, like just one more day after that, and he wrote, quote, life would be a lot easier if we could turn checksums on and off without re-initdbing. And no one objected to that. And he further sort of goes into that email, like what would that even look like? And he outlines sort of a process like this. Something starts, something reads every page, calculates the checksums, rewrites it, and then it checks, am I done? Are there any new pages that I need to do? And when you're done, you're done. Checksums are on. But there's a problem here, in that during this period, checksums are neither on or off. They're in this sort of Schrödinger state of, we don't really know, because they're not on, but they're also not off. But in his original email, he actually outlined a process that kind of is what we have today right now, where he says, if you take one bit in the checksum version field and mean it in progress, so when checksums are in progress, Postgres will compute and write checksums whenever they write a buffer, but it will not verify checksums on read. So essentially, you get into a system where you can write a checksum, but you're not going to verify them when reading because they might not be correct yet. And at that point, we still have this. We have a system where every process in the Postgres cluster knows what to do at any one given point in time because they know they have to write a checksums, but they are not allowed to verify it. Or they have to do both, or they should do neither. So here's the sort of like the basic architecture of the whole premise. And then essentially nothing happened for another year. until we had coffee at a user group meeting in 2018 and figured, like, how hard can it be? Let's just get it done. And we sat down and hacked a bit of code. And about a month later, we posted it to hackers. So this is early 2018 at this point in time. And it was roughly, just north of 1,700 lines. It could do online enabling and disabling of checksums. It fully handled replicated clusters. It supports process throttling, because essentially at this point, like, you're shipping your database through the wall stream. So being able to at least limit the amount of I/O incurred is obviously a good idea. It had an offline verification utility called pgverify checksums, and it had tests and documentation. So it was the complete package. And it looked like this. There's a SQL level function that immediately returns, and the way to check progress is to simply look at the GUC data checksums. And during this, the processing, it starts a checksum helper, which will go through every database, every relation in that database, every data page in that relation. And if the checksums doesn't match, it will rewrite the page, dirty the buffer, rewrite the page, thus setting the checksum. And it just basically go on and on and on until you're done. And at the end, it flips the value of data checksums to on, thus making every process knowing what to do, read and write. So far, so good. Disabling is obviously a lot easier because there's no I/O. We don't need to zero out the checksums. We could, but we don't want to do that. We can just flip the value in PG control and we're done, or so we thought. But that was the idea, and it kind of works. You flip the value, now checksums are off. Easy, no I/O. So on this patch, we had a lot of good review coming through. We had some goalpost shifting, which was mostly at this point contained, and it was eventually committed prematurely. And post-commit review found a couple of issues with this. For example, why does it return true? It's not done. This optimization doesn't work. You can't change the throttling. That doesn't work, that doesn't work, that doesn't work. Like, nothing worked, really. Unless you were in sort of the happy path. So the patch was reverted, and a small matter of program was required to fix this, and that only took roughly 7 years. But we're here now. So I would like to talk about what was the problems that were sort of in the original patch and how we overcame them. And they're briefly grouped by synchronization, replication and replay, testing, and sort of project management aspect of it, where we had a few issues. So starting with synchronization. The first version of the patch used atomic updates on a flag value in shared memory to synchronize this whole processing. And when you look at it, Postgres is really just a distributed system. You have all these distributed processes that you need to synchronize across. And distributed systems are really hard. And locking protocols for distributed systems are also very hard. And we got it wrong. But it didn't actually matter because the atomic operations were also not concurrency safe. So we couldn't get it right anyway, turns out. But even that wouldn't matter because in the period when it was committed, the build form broke because it turns out the atomic operation fallbacks that we had were completely broken and didn't work at all. So it's like 3 levels deep of failures here. But the good part is we fixed the atomic operation fallbacks, and now those works for those platforms who doesn't have those. Right. And in that thread, Andres posed the hypothetical question, I wonder if we could introduce a mega expensive rare memory barrier to essentially go through PGProc, signal every process, signal that they require a memory barrier. And that's a key piece of this puzzle here, right? Because obviously the most mega expensive barrier is a restart. But that sort of defies the whole point of an online operation if you have to restart your cluster. I mean, sure, it's not an offline, but it's also not online if you need to restart. So obviously that wasn't good enough. But Andres was pestered enough by Magnus to actually implement this. So he implemented proc signal barriers, which is a process synchronization parameter that we really didn't have anything like that in Postgres. And now we do. And I'll go in a bit of detail of what they work, how they work. But from starting with the second iteration of the patch, we converted everything to use proc signal barriers, and that's still true today. And funnily enough, they exist because of this patch, But there were already 2 other consumers when I committed this. 2 other use cases that were made possible because of the infrastructure brought on with this patch. So that I consider that a pretty big win. So they were committed in 2019, at the end of 2019 by Robert, and they work basically like this. Assuming you have some sort of synchronization process, you have lots of backends, and you want to flip the state of the cluster. So what you start with doing is you emit the proc signal barrier. You emit the barrier, and then you go to sleep, expecting to be woken up when the barrier has crossed. And then all the backends will absorb the barrier at their own leisure. And only when the final one has absorbed the barrier is the synchronizing process woken up. And at that point, you know that the state of the entire cluster is guaranteed to have progressed past the barrier. So in this case, for us, that meant everyone is now in progress, which means that everyone is writing checksums, but not reading them. And this is a really strong synchronization primitive, which works really, really well, and has a super simple API of 2 functions. Cool. So, as I said, they ensure consensus on a state reached across a cluster, but it's important to notice that this is not a processing barrier. Like you're not processing anything with the barrier. You're just absorbing it and going on. Processing has to happen in another process. This is only for backends to acknowledge, I have seen this state changed, I've applied it, and I've moved on. And there is no guarantee on how long this process takes. It might take a millisecond, it might take a million seconds. You don't know, and you're not supposed to write code that relies on it being fast or slow. So, another problem with the synchronization, I said earlier that disabling checksums is easy because we don't do any I/O. We can just flip a value. But that's a very short window, but every window can be broken. And sure enough, this can too. So what we did was essentially this. Let's say we had 2 backends. We flipped the value, and they at some point going to read the PG control, which is really fast, but not fast enough for someone to write a page. And at that point, they're not going to update the checksum because this guy already knows that we're off. And then this process will read it, figure out that it's wrong, get a page verification failure. And I mean, we're talking wall clock time. This is tiny, but it's actually pretty easy to hit it. So again, proc signal barriers were used to fix this. We split the in-progress state into in-progress on and in-progress off, meaning that disabling checksums is essentially exactly the reverse of enabling them minus the I/O. We still don't have to rewrite all the pages, but we have to go through the same state machine updates to make sure that everyone in the cluster agrees on the state change. So that made disabling work. So now what it looks like is this. We're in progress. So even though this guy knows that it's progress off, when he updates, he's going to update the checksum. And when this guy updates the checksum, writes the same page, he's still going to update the checksum even though everyone else is in off. But that doesn't matter. He's in progress off. He has to do it. Another problem, we had some issues with replication. Now, the original code looked like this. It would calculate the checksum on a page, and it would check, does it match what is already written on the page? And if it doesn't, dirty the buffer. But if it does, well, that's a good optimization. We don't have to dirty the buffer. We can just move on. And it turns out that's wildly incorrect, because we don't know what's on the standby. We only know that that works for the primary, where we're operating. But the standby, there is no guarantee that this checksum matches on the standby. So again, it was something that was seemingly obvious, and most reviewers just, okay, that's clearly right. But when you start getting into the very nitty-gritty details, turns out you need to dirty all buffers, regardless of if they're all correct, because we simply have no guarantee of the state on the standby. So that was another issue we found and fixed. Replay. Let's say we have this situation here. We were moving from off to in progress on to on. Everything is fine. At the end of it, we're going to rewrite PG control and update the state to say, yep, checksums are now on. Great, everything works, except then Postgres crashes. Fine, Postgres can handle a crash, no worries. Well, what if the restart point is there? And PG control is read during redo. Oh, checksums are on. Great. Now I'll start replaying. Oh, every wall record has no checksums in them because they're off. And that's a problem because we're not dealing with incompatible data durability models. PG control is written like just a frozen point in time when the wall stream moves on. And this was a thorny one this was a pretty hard one to crack. But again, Andres had a good idea of basically moving the checksum state into starting a recovery. And while he was expecting us to not use any checkpoints, that turns out we actually had to. But the gist of the idea stays that every state change enforce a restart point, which means that whenever you're restarting, you will always restart on a state change. You will never have multiple state changes between a restart and where you are. Create checkpoint will store the state in the reader record, and xlog redo will apply that during redo to make sure that you're always going to be in the state where the cluster was when it crashed, or sort of during that when it was in the real wall stream. So replay will always use the value from the wall stream and will disregard what PG control says. So I'm trimmed down a bit for size because xlog.c is about 5 million lines long. But essentially, this is what happens. During redo, if we find a checkpoint reader, we're going to copy the checksum version into shared memory, into local memory. And if that turns to be a new state compared to what the control file said, guess what? We're going to change the state of the cluster. We're not going to trust the PG control file. And the same thing during redo, then when we actually hit the checksum record for changing the state in the wall stream, again, changing the state and updating shared memory. So in hindsight, this might seem like an obvious solution, but changing redo records is not for the faint-hearted. I mean, touching anything in xlog.c is terrifying, and changing replay is like magnitude worse. But thankfully, Andres had the idea, persisted, and it works. So, I mean, it was Andres' idea, so obviously it works. Testing was also really hard, because writing tests that orchestrates multiple concurrent processes, each doing different things, to hammer a system is exceedingly non-trivial, and especially back then in 2017, it was really hard. And the initial patch it really, really abused the isolation tester because it was the only thing we had that could run multiple processes and orchestrate them. Clearly, that had to be written as a tap test because that didn't fly for any reviewer. But it was the only thing we had at the time. Now, it is important to notice that it is simple to test this under the happy path, but production is really messy and anything will break in production. So it has to be tested with sort of incomprehensible barriers. Like it has to be tested with making window, like any race condition window has to be a moving target because otherwise you're just going to test a happy path all over and over again. So, and to be fair, all of this was possible all along just using the IPC run module. But IPC run as just a bare module is hard to use, right? It's not easy to use. The PostgreSQL test background PSQL was a huge improvement in this because it gave us a very simple API for running background PSQL workers, like just sort of spawning them off, giving them some work to do while continuing to test another process. So that was a huge, huge change, much bigger than we thought at the time, I think, when we committed that. Because it made orchestrating multiple backends a lot easier for testing. And then came injection points, which was a real game changer for this. Because it made testing these hard-to-reach error paths possible in a controlled and repeatable way. So you could really test like those error handling that you're basically previously just saying, well, we hope it works because we can't really fudge them or synthesize them in testing. Now we can. And you can even sort of single-step a state machine in a tap test by sort of injecting a injection point, but pausing the whole thing, injecting global, like checking global state, and then moving on. So, and also obviously injecting randomness and just overall making life really hard for your code. It was truly, I don't think we could have committed this code without injection points, for sure. And also, like, you can call abort in the really worst place possible for your code. You can easily just make it completely crash and ensure that your durability fixes handles that. So that's really cool, really good. And it made, as I said, I don't think we could have done it without injection points. So a little bit about the sort of the project side of this. This patch was immediately criticized for being too complicated and not complicated enough. And I think that's a pretty human thing, right? Because this feature had been discussed on the list many times in the past. Like, this was not the first attempt at doing it. You can go back to 2015 and find even earlier attempts at this, which means that a lot of people have been thinking about it for a long time. They have a mental model of what it should look like, and immediately, if what we proposed did not match that mental model, surely, they're going to tell you that, right? So anything that's been discussed for a long time, there is an increasingly big risk for scope creep. And I think that's very human. I don't think that's a fault of the project, and it's not a fault of anyone in particular, but it's something to really watch out for, because this patch was huge to begin with. Making it bigger was just sort of, it would never work. And to avoid burnout in situations like this, I think it's really important to get collaborators on a patch. When a patch goes on for years and years, like, just get more people involved. It is invaluable to keeping motivation up. And I think Bruce summarized it pretty well when he said, quote, "I don't think anyone has done anything wrong, rather it's what we're trying to do that is complex, and adding restartability is just added to the challenge." This was as a comment to a big push at the time to add a restartability feature to this, because currently, if you're enabling checksums and you crash, well, you have to start all over again. That's not good, but making that work with restartability is like, it's an order of magnitude harder than making it work at all. So it is what it is. I mean, I don't think anyone did anything wrong. It's very important when reviewing code to make sure that you keep the goalposts in sight for the author. Then it eventually got committed. And it's actually the same basic functionality and overall architecture that we had in 2018. Everything beneath that changed, but pretty much what the users saw is exactly the same. That it doesn't have restartability, it has very few optimization, it simply is focused on making the basic scaffolding for this work. It has the state transitions of off, in progress on, in progress off, and off, as discussed earlier. It uses proc signal barriers for synchronizing it, and it has an extremely extensive test suite. So big that most of it is actually disabled by default, because it will take way too long to run. But you can enable it pretty easily with pgtest extra. So, with that in mind, what is sort of next? Like, is there a next step for this, right? I think there is. I think currently there's only a single worker processing the entire thing in sequence. If we have multiple workers, it's going to be a heavier tax on the I/O, but maybe that's fine for someone. Now, at least people should have the ability to choose. Right now, it can only have one worker. There's a launcher and a worker. We don't have a reader-only verification mode online. I mean, Postgres hasn't had that ever. Now we could have it. There's already some work on improved state handling. Tomasz is doing a lot of work there, and he has an amazing patch on testing, which everyone should go check out, because it's really cool about, so I said, single-stepping a state machine with ejection points. And also restartability, if someone wants to spend 7 years working on a patch. So then the question is, was it worth it? It went from 1,700 lines of code to 5,100 lines. It took 256 million seconds to do it. And it landed in a place where checksums are already on by default. And we have a tool available to do it for a long time. So was there a point to all of this? Like, was it actually worth doing? And I would argue that it was, obviously. There's still lots of pre-18 clusters out there that don't have checksums. I don't think we should have any functionality require offline mode or single user mode. That is not something we can do in a software as a service world. And also, previously we couldn't add a new checksum algorithm because we couldn't migrate it to it. Now it's simple. All the functionality for doing that exists. You can simply add a new checksum algorithm, migrate your database to it, and you're done. And also, we don't have a way to verify checksums in a database online. And now we can add one very easily. So on that note, I'm done because I'm out of time. But I would like to say thank you to Magnus, Tomas, Andres, and Heikki, because without them, this patch would never get committed. So thank you very much.